In earlier videos, I've been asking, why is C sub p higher than C sub v? And I think that question has something to do with if you think about the quantity change in heat over change in temperature. Or to be more notationally correct, that would be Q over the change in temperature. And I'm also going to plug in a N for the number of moles of the particle, and that is the specific heat at constant volume or the specific heat at constant pressure. Now I think the real reason that these are different is mainly well, an application of the first law of thermodynamics. If you've been watching the corrections to my earlier videos, you know that the heat applied to the system is kind of divided up into two parts. First, some of the heat goes into changing the internal energy of the gas, and the other part of it goes into doing work on the environment. On the other hand, another perfectly good interpretation of the first law of thermodynamics is that the change in internal energy of the gas, this is an effect, basically. I think of it as an effect. The change in internal energy is going to be equal to the heat added to the gas plus the work done on the gas. So these are two perfectly valid interpretations of the first law of thermodynamics. These are basically the same equation. However, these equations become intuitive under specific situations. This equation here is intuitive when you have an expanding gas, and this equation here is more intuitive, I think, when you're compressing the gas. That clarifies that a little bit, but now let's clarify the difference between C sub p and C sub v, and we can make a little restriction on here. When we have something at constant value or constant volume, then the work done on the environment and the work done on the gas is equal to 0. So we can make this simplification to this equation that delta U equals Q. The heat added is equal to the heat in the internal energy change. And that internal energy change was found, we did that in chapter 10. We actually found that the internal energy of the gas was actually the same as the kinetic energy of the gas, but only not the whole kinetic, no, it was the whole kinetic energy. It was the total kinetic energy of the gas. On the other hand, C sub p is governed by this equation here, Q equals delta U plus WENV, but the work on the environment is just pressure times the change in volume. Now there's some kind of connection that I really need to make right here, and I believe it has something to do with replacing that P delta V with use the ideal gas law and say something along the lines of this is going to be nR delta T. That is, assuming that the number of particles stays the same, which when you're dealing with specific heat at constant pressure, it generally is. And really, I need to put together that whole equation that I've been kind of floating around. This one, PV equals nRT equals 2 divided by the degrees of freedom times U. And U is just the total kinetic energy. The reason I like this equation is I believe it is always true. Or at least in any case where you've got gases, possibly even non-gases, because a solid would just be essentially a something with a smaller number of degrees of freedom. But yeah, I don't think that PV part, this equal sign, wouldn't hold in the case of a solid. So here's the key. We're going to think in terms of deltas, and I want to replace that delta U with and basically this equation here, change nRT to nR delta T, change 2 over dF to 2 over dF delta U, and then solve that for delta U, and we'll have delta U equals degrees of freedom over 2 times nR delta T. And we'll just plug that in over there to get Q equals this delta U, degrees of freedom over 2 nR delta T, plus this thing over here, which should just be plus nR delta T, which if you do a little bit of algebra on it, it'll be dF plus 2 over 2 nR delta T. So that pretty much gives it to us. I'm going to make a couple of subscripts in here just to keep in mind. This is the heat added at constant pressure. So and this is the heat added up here, the heat added at constant volume. So think in terms of heat added at constant pressure and heat added at constant volume, and the difference is that Q sub V is only going to have in it this part, the degrees of freedom over 2 times nR delta T. And the Q sub P is also going to contain this pressure times change in volume term, which is the same as nR delta T, which is the same as, well, yeah, nR delta T. So when we take the heat exchanged divided by the number of moles and the temperature change, on this side we'll get dF plus 2 over 2 times R, and on this side, so that's C sub P, the specific heat at constant pressure, and on this side we'll get Q sub V over N delta T, which is going to just be degrees of freedom over 2R, and that is C sub V. So that is about as good as I can do at this point, explaining why C sub P is dF plus 2 over 2 R and C sub V is dF over 2 times R. It's this work term that's involved that just happens to also be nR delta T. In the constant pressure, you've got that work. In the constant volume, you don't have that work. So the energy you save by not expanding the gas goes into increasing the temperature of the gas, which is down here.